Hi students. Here we are going to learn about a new type of theorem called as maximum power transfer theorem. Okay. So this theorem, from the name itself you can understand maximum power transfer. That is, this theorem is used to determine the value of the load impedance. That is this value over here. The value of the load impedance for which the source will transfer maximum power. That is, this theorem we are basically using if you want to find the maximum power you can extract from the source. If you want to know how much power, what is the maximum limit or what is the maximum power you can take from the source, then that depends on the type of the load you are going to use. Okay, so depending on the load, depending on the type of the load, you can extract maximum power from the source. That is what this maximum power transfer theorem is usually used for. Okay, so basically for this circuit form, if you want to find the maximum power from the source, what you basically connect is you basically connect a variable load. Okay, so this is a variable impedance. A variable impedance means this can either be a resistor or a capacitor or an inductor, or a resistor with a capacitor, resistor with an inductor, or resistor, or it can be any impedance. Okay, and the source is also a complex impedance, which means it has also also have a resistor and a capacitor and an inductor. And this voltage source over here is also a complex number. Like for example, it can be 10 angle 30 degree, or it can be 5 angle 30 degree, or it can be 5 volt, or it can be a DC voltage also. Okay, so in whatever case it is, depending on the load impedance, okay, depending on this load impedance, you can extract maximum power transfer, you can extract maximum power from the source. That is why this load is a variable load, because if I want to have maximum power, I need to change the value of my resistance or the value of my reactance, value of my resistance or my value of my reactance, right? And from there I can get the maximum power from the source. So what is the equation for power? What is the equation? What equation you are going to use to find the value of power? The equation you need to use is that, see here, the power is mostly delivered through the load resistor RL, right? Or we know that, right? Heat energy is always dissipated through this resistor RL, to the resistor RL. So therefore, the equation for power we are always using is this equation, that is PL is equal to magnitude of IL the whole square into RL. This is the equation of power. We know that power is equal to I square R, right? Power is P is equal to I square R. That's the equation you have learned from school. The same equation over here, where IL is the current through the load. Okay, and IL is specifically the current through the load resistor RL. So the IL is the current through the load, and we need to find the magnitude of that current. The magnitude of that current square multiplied with the resistor RL will give you the power. This is the equation for power. So this theorem is used to find the maximum value of this quantity over here. This theorem is used to find the maximum power through the load. This is given from the source, that is transferred from the source. Okay, so the thing about this is that in order to find the maximum power transfer, in order to find the maximum power that you can get from the circuit, you need to consider the type of variable that you're using over here. You see, when I say a variable impedance, what is the meaning of this? This is a variable, this is a load impedance which is variable, or this is a variable load impedance. ZL, let me call this as a name as ZL. Okay, ZL is equal to RL plus JXL, which means ZL is equal to RL plus JXL is what you call as this one. That is, this is the variable load impedance. Now, why do I need it to be a variable? Why do you need a variable load impedance and not a fixed load impedance? Because if it is a fixed load impedance, you cannot change the value, and if you cannot change the value, you cannot find what the maximum power transfer is. You cannot find what the maximum power is. You see, if you fix a variable load over here, a variable load, then you can change the value of the resistor or a rheostat or a potentiometer, or you can use a variable capacitor, or you can use a variable inductor. You see, if it is a variable load, you can change the value of the load in such a way that you can get maximum power from the source. That is why it has to be variable. Okay, so in every case in maximum power transfer theorem, if you want to find the maximum power, we connect a variable load at the end of the circuit, for our calculation purpose. Okay, so what is the meaning of variable load? You see, every impedance has a resistance, a capacitor and an inductor, right? So that is what is written over here. This is definitely a resistor. RL represents the load resistor that is connected over here, which is always there. Therefore, there is always a resistor inside the circuit. Over here, the load impedance will always have a resistor, because without the resistor, we cannot calculate the power. We need the resistor to calculate the power. So resistor will always be there, and this XL reactance, this can either be a capacitor, or it can be an inductor, or it can be a capacitor with an inductor, or it can be no capacitor, no inductor. In that case, the value of XL will become equal to 0. See, this is what. So therefore, depending on the type of the variable load, there are three cases. There are three cases in which you can apply this theorem. The first case is case 1. Case 1. And that is when the ZL is nothing but a variable resistor. When your load impedance, when the load impedance is nothing but a variable resistor, then what is your maximum power transfer theorem? We need to find that. That is the case 1. Case 2 is if the load impedance has a variable resistance and a variable reactance. If the load impedance is a combination of a variable resistor and a variable reactance, that is case 2. And case 3 is when the load impedance is a variable resistor but a fixed reactance. This means that here RL represents this RL over here is variable. Okay, this RL is variable. In case 1, we'll assume that the load impedance is a variable load resistor. In case 2, we will assume that the load impedance is a variable resistor and also a variable reactance. When I say variable resistor, it can either be a rheostat or a potentiometer. When I say variable reactance, it can either be a variable capacitor or a variable inductor. And the third case is that when the load impedance is having a variable resistor, but the reactance cannot be changed. The reactance is fixed. These are the three cases, and depending on these three cases, the maximum power transfer theorem will change. So what is the maximum power transfer theorem? When the load impedance is a variable resistor, you need to find that. The case 2 is what is the maximum power transfer theorem? When the load impedance is a combination of a variable resistor and a variable reactance, that is case 2. And case 3 is that what is the maximum power transfer theorem? When the load impedance is a variable resistor but a fixed reactance. Fixed reactance means we can't change the value, it's fixed. This is our three cases. So we will evaluate each of these three cases. Okay. So this is case 1, when the load impedance is a variable resistance. So as you can see over here, this circuit consists only of a voltage source with a series impedance and with a load impedance over here. Okay, and you should understand that basically all these things are considered as a complex numbers, right? Including this Vs it can be an AC voltage or a DC voltage. It can be simply a 5 volt or a 10 volt, or it can either be 5 angle 30 degree or 10 angle 90 or whatever. Okay, and this is nothing but a combination of a resistor and with an capacitor or an inductor or any one of these three elements. Okay, and this is important. This is the variable impedance, and in this case, in case 1, this is nothing but a resistor, a variable resistor. It can either be a rheostat or a potentiometer. And what you're going to do is you need to find the equation of power from this circuit. And we all know what is the equation of power, right? The equation of power is PL is equal to IL square, magnitude of IL square into RL. This is the equation of power through the load, which is the equation you need to find. To find this, you need to find the magnitude of IL. To find the magnitude of IL, you need to find what is IL. And what is IL? IL is the current through the load. So first I will find the value of IL. So I am going to apply mesh analysis in the circuit. So therefore, I can say that IL into, if I am applying Kirchhoff's voltage law, right? So then IL into ZS and ZL. So ZS plus ZL is equal to Vs. This is Kirchhoff's voltage law. Okay. And what is ZS? Rs plus JXS. So IL into Rs plus JXS plus, and what is ZL? ZL is RL plus RL is equal to Vs. So if I'm going to write it in terms of real number plus imaginary number, then in that case IL into Rs plus RL plus JXS is equal to Vs. Or in other words, the equation for IL is Vs by Rs plus RL plus JXS. This is the equation of IL. And you remember, this whole thing is a complex number, right? Because everything over here, every elements over here is considered as a complex number. So this is a complex number, which means if you want to find the magnitude, you need to find the magnitude of both the numerator and the denominator. How to find the magnitude? We all know that, right? What magnitude means, if A plus JB is a complex number, then the magnitude is given by A square plus B square. That's the magnitude. Or if you are finding the magnitude, if it is the polar form, R angle theta. If it is in the polar form, then this itself is the magnitude. This magnitude written over here, excluding this angle. Remove the angle and you will get the magnitude. This is the two ways of finding the magnitude. If these two are the same number, we know that a complex number can be either be represented in a rectangular form or can also be represented in polar form. In that case, if these two are the same, represent the same number, then R is equal to root of A square plus B square. So now here I am going to find the magnitude of IL. So to find the magnitude of IL, the magnitude of Vs, if Vs is a complex number, then magnitude of Vs is how I am going to write to express the magnitude of Vs, or magnitude of this complex number. So the numerator is magnitude of Vs, and what about the denominator? The denominator, this is the real part. Rs plus RL is the real part and XS is the imaginary part. So therefore it is root of Rs plus RL the whole square plus XS the whole square. This is the magnitude of the denominator. So this is the magnitude of IL. This is the equation for magnitude of IL. And I am going to substitute this equation over here. So therefore I will get PL is equal to, on substituting this, what will I get? This is magnitude of Vs the whole square by, and here square means this square root will disappear. So you will have Rs plus RL the whole square plus XS the whole square into RL. This is the equation of the power. So now I have found the equation of my power. Okay. So now you need to find the maximum power, right? Or what you need to do is you need to find the value of RL such that PL is maximum. You need to find the value of the load resistor such that the this power over here is maximum. So how do you do that? We have already learned these kind of things in mathematics, right? If you want to find the maximum value of any quantity with respect to another quantity, just simply need to differentiate it with respect to that quantity and equate it to 0. So here, if you want to find the maximum, if you want to find the value of the load resistor such that to get maximum power, all you need to do is, for power to be maximum, comma, then all you need to do is simply differentiate it, this equation, this power equation with respect to that element, which is RL, and equate it to 0. This is how we find the maximum power. Okay, or this is how we find the value of RL so that you will get maximum power. Simply differentiated that power with respect to that resistor and equate it to 0. Okay, so what is the equation for PL? This is the equation for PL, right? So therefore I can say that d by dRL is, and PL is this one, that is Vs the whole square into RL by Rs plus RL the whole square plus Xs the whole square is equal to 0. Okay, this is the equation, right? This I can take it outside, so therefore this Vs square is constant, so I can take it outside, so therefore this will become magnitude of Vs the whole square into differentiation of with respect to RL of RL by Rs plus RL the whole square plus Xs the whole square is equal to 0. Okay, so basically so how I'm going to differentiate, you can differentiate any way you want. I'm going to differentiate in such a way by applying the u by v equation, right? We all know that equation, that is the differentiation of a function of u and function of v. U by v is given by v into du minus u into dv by v square. This is the equation, v into du minus u into dv by v square. This is what I'm going to say here. V is this denominator and u is this numerator. So therefore, let me see, this will become magnitude of Vs the whole square into, and here you have V is this term, that is Rs plus RL the whole square plus Xs the whole square. This is V, and du. Du is differentiation of RL with respect to RL is 1 in, it becomes 1 minus, and u is RL, and then the differentiation of the denominator, which is let me see, 2 into Rs plus RL plus 0. So it is 2 into Rs plus RL. This is the differentiation of the denominator by V square. V square is the denominator, which is Rs plus RL the whole square plus Xs the whole square. Okay, and again the whole square, and this value is equal to 0. Okay, so this is a constant and this is a denominator. If I bring this constant over here, it will become 0 by Vs square. 0 by Vs square is 0 itself, and if I put this also in the other side of the equation, this into 0 is 0 itself, which means only the numerator is left behind. So therefore this is nothing but Rs plus RL the whole square plus Xs the whole square minus 2RL into Rs plus RL equal to 0. Okay, I'm going to expand this, so this will become Rs square plus RL square plus 2Rs RL plus Xs the whole square minus again 2Rs RL minus 2RL square is equal to 0. Okay, and these two terms will cancel each other out. This one over here and this one over here will cancel each other out. So you will have the equation as Rs square and RL square minus 2RL square is minus RL square plus Xs square is equal to 0. Okay, which means you need to find the value of RL square. Right? So what is RL square? RL square is equal to Rs square plus Xs square. This is the equation of RL square. So which means RL is nothing but the root of Rs square plus Xs square. This is the equation, right? What is Rs square plus Zs square? We all know that Zs is equal to Rs plus Jxs, right? So therefore magnitude of Zs is nothing but root of Rs square plus Xs square, which is this itself. Therefore this is nothing but RL is nothing but magnitude of your source impedance Zs. So what this equation represents, that this equation means that if you want to have maximum power to be transferred from the source, then the value of ZL or the value of RL must be equal to the magnitude of this source impedance. That is what case 1 means. Okay, case 1 means that if you want to have maximum, in order to achieve maximum power from the source, the value of the load impedance must be equal to the magnitude of the source impedance. This is the first equation you have studied. This is case 1. Okay, this is what case 1 means. Now we will look at case 2. All right, so this is case 2, when the load impedance is a variable resistance with variable reactance. Okay, so here basically this whole thing again, and like I said, everything is the same voltage source with a series impedance, and here across the load we have a variable. This is also a variable load impedance, but in this variable load impedance it consists of a variable resistor with a variable reactance, which means this resistor can either be a rheostat or a potentiometer, and it is variable. Variable means you can change it, right? You can change the value to suit according to your needs. You can change the value, and this variable reactance, right? Which means it can either be a variable capacitor, or it can be a variable inductor, or it can be a variable capacitor and a variable inductor, or any one of them. Okay, so that is what it means. So both of them, this is what it means. That means both the real part and the imaginary part are variable. That's what this means. This is case 2. So let me apply. So we know that the value of power, right? If you want to find the value of power, it is nothing but power across the resistor, and the resistors again it is RL. So therefore it is IL square, magnitude of IL square into RL. This is the equation, which means you need to find the equation for IL. So that means IL is the current through the load, which in this equation, if I am going to apply mesh analysis, then the value of the equation of IL is IL into ZS plus ZL is equal to Vs. This is the mesh analysis of this circuit, right? And what is the equation for ZS? The equation of ZS is Rs plus JXS plus, and the equation for ZL is RL plus JXL. RL plus JXL is equal to Vs. Okay, this is the equation. Let me combine the real part and the imaginary part. So the equation will become IL into Rs plus RL plus J into XS plus XL is equal to Vs. So in other words, the equation for IL is equal to Vs by Rs plus RL plus J into XS plus XL. Okay, this is the equation. So which means if you want to find the maximum power of this equation, then or if you want to find the magnitude, first you need to find the magnitude. So the magnitude of this is equal to magnitude of Vs by, so this is the real part, this is the imaginary part, so therefore it is root of Rs plus RL the whole square plus XS plus XL the whole square. Okay, this is the magnitude of IL. Okay, this is the magnitude of IL. So which means if you want to find the maximum, if you want to substitute this equation over here, so therefore this equation will become PL is equal to magnitude of Vs the whole square into RL by Rs plus RL the whole square plus XS plus XL the whole square. Okay, this is the equation of the power. Okay, so one interesting thing about this, one of the easiest thing about this to understand is that both the terms are variable. This is variable, this is also variable, but this is the value you need to find, right? You need to find you can't change this, because if you change this, you are basically changing the power value of the power. So you can't change this, you are going to change this one, but you can change this, right? This is a variable reactance, and if you look very carefully over here, if you want to have maximum power from the circuit, if you want to have maximum power from the circuit, then this denominator must be very small, or you should make the denominator small. right? Or you to change the value of the denominator such that it can be small. So in that case, what you're going to do is, in order to get maximum power, you got to reduce the value of the denominator. So to reduce the value of the denominator, what I'm going to do is that I'm going to put XL is equal to minus XS. I'm going to put XL is equal to minus XS, because if I do like that, then the denominator will become small. If the denominator becomes smaller, then this power will increase, right? The value of the power will increase. So this is what I'm going to do. That is to have maximum, to increase power, comma, XL is equal to minus XS, so that the denominator becomes smaller. So in that case, the value of PL is equal to magnitude of Vs the whole square into RL by RS plus RL the whole square. Okay. So if you're asking me, how can I do this? What is the reason that how can I simply change the value of my reactance like this? Is because this is a variable. Variable means you can change the value however you like, right? You can change the value which however you find convenient. You can simply change the value of your reactance because it is also a variable. So what you need over here is a maximum power. So if you want to have maximum power, then you should make the denominator smaller. So one of the ways of making the denominator smaller is by putting the value XL is equal to minus XS, because I can change the value XL to any value I like, right? It's a variable, so I can change the reactance to any value I like. So I'm going to change the value to XL is equal to minus XS, so that this term will cancel each other. So if this term cancel each other, then the denominator will become smaller. That's how I can increase the value of my power. That's why this equation has been, now it became like this. So what I'm going to do is I'm going to find the value of RL so that maximum power can be extracted from this equation, right? This quantity will become maximum. So in that case, what I'm going to do is I'm going to find to have maximum power, comma, again I'm going to differentiate it with respect to RL and equate it to 0. This is what I'm going to do. So therefore this is nothing but, let me see, there is d by dRL of magnitude of Vs square RL by RL plus RS the whole square should be equal to 0, or this Vs square is a constant, so I'm going to take it outside, so this will become Vs the whole square into, and here also this is basically nothing but d by dRL of RL by RS plus RL the whole square, right? So again I'm going to apply U by V equation, right? So this also, if I put this thing on the other side of the equation, this will become 0, so this will get cancelled. So therefore this is nothing but d by dRL of RL by RS plus RL the whole square is equal to 0. So therefore V into du, V is RS plus RL the whole square, V into du, and differentiation of RL is 1 into 1 minus U RL into dV. dV is 2 into RS plus RL, right? Into 2 into RS plus RL by RS plus RL see over here, RS plus RL the whole raised to 4, right? Square the whole raised to 4 equal to 0. Okay, now this term, if you comes over here, this into 0 is 0 itself, which means only the numerator is left behind, which is rs plus rl the whole square minus 2rl rs minus 2rl square equal to 0. And here it is nothing but rs square plus rl square plus 2rs rl minus 2rl rs minus 2rl square equal to 0. And this rl square minus 2rl square is minus rl square, and these two will cancel each other. So basically you have rs square minus rl square equal to 0. Therefore rl square is equal to rs square, or in other words rl is equal to rs. Which means if you want to have maximum power, from the source, and if you have a load which is both a variable resistance with a variable reactance, then the value of RL must be equal to RS and the value of XL must be equal to minus XS. In other words, the value of XL is equal to minus XS. If you want to have maximum power, then these two conditions must be satisfied. Or in other words, the value of ZL, we know that ZL is equal to RL plus JXL, right? And what is RL? RL is RS itself. And what is XL? XL is minus XS, which is minus JXS. So which means, what is this RS minus JXS? We know that RS plus JXS is equal to ZS, right? And in that case, what is RS minus JXS? It's nothing but the complex conjugate of ZS. Alright, so which means ZL is equal to ZS star. ZL is equal to ZS star, which is RS minus JXS. Which means if you are having a load which is a variable resistor with a variable reactance, and if you want to have maximum power, then the value of the variable load impedance must be nothing but the complex conjugate of your source impedance. If you want to have maximum power, this should be the value of your load impedance, which means it has to be a complex conjugate of your source impedance. So whatever the value of your source impedance is, let it be any value. If you want to have maximum power from that, and if you are having a variable resistor with a variable reactance, then that variable impedance must be equal to the conjugate of that source impedance. This is what case 2 is telling us to do. Okay. So this is case 2. So this you can only apply this when both the resistor and the reactance are variable. Right? You can't touch the resistor, because if you can't change the resistor, if you change the resistor, you are basically changing the power also. So you can't touch this, but you can change this, and that's how I changed it. In order to reduce the power, in order to increase the power, I reduced the denominator by putting XL is equal to minus XS. And then I again differentiated it, and then I found the value of RL, and then from there I can understand that if you want to have maximum power, then the value of RL must be RS and the value of XL must be minus XS, which is nothing but the value of the load impedance must be a complex conjugate of your source impedance. Okay, so this is what case 2 is telling us to do. Now we look at case 3. So now case 3 is when the load impedance is a variable resistance with fixed reactance. So here basically the circuit, everything, like I said before, it's all are complex numbers, but here in the load impedance, only the resistor is variable, which means you can only change the value of the resistor at the end, but you cannot touch the reactance, because the reactance, just like this reactance over here, this reactance is fixed. It's simply a fixed capacitor or a fixed inductor or a combination of these two. So you can't change the value of the reactance. Okay, so let's, as usual, we know the equation for power, right? PL is equal to magnitude of IL the whole square into RL, right? This is the equation for power, and the equation for IL is IL into ZS plus ZL is equal to Vs. IL into ZS plus ZL is equal to Vs, just like your mesh analysis. Okay, so we know what is ZS. It is Rs plus JXS plus, and ZL is RL plus JXL is equal to Vs. Okay, and let me write it in terms of complex number, which is Rs plus RL plus JXS plus XL is equal to Vs. So therefore IL is equal to Vs by Rs plus RL plus J into XS plus XL. Okay, and therefore the magnitude of IL is the magnitude of the numerator, that is magnitude of Vs, by, and the magnitude of the denominator is root of Rs plus RL the whole square plus XS plus XL the whole square. This is the magnitude of IL. So which means I'm going to substitute that over here. So therefore PL is equal to magnitude of Vs the whole square by, and here it is Rs plus RL the whole square plus XS plus XL the whole square into RL. Okay, this is the equation. Now one of the bad news about this is that in case 2, in order to change the value of power, in order to increase the value of power, I made XS is equal to minus XL. I changed the value of XS is equal to minus XL so that the denominator will be reduced so that I can increase the value of power. Here I cannot do anything like that because the reactance is fixed, which means I cannot touch this. I basically cannot touch the value of XL. So therefore I cannot make any changes equation. So all I can do is I can simply find the value of RL so that this power is maximum. So all I can do is simply differentiate it with respect to RL, right? That's all I can do over here. So therefore, let me write that first. To get maximum power, comma, dPL by dRL is equal to 0. Okay, or in other words, differentiation of with respect to RL, magnitude of Vs the whole square, magnitude of Vs the whole square into RL by Rs plus RL the whole square plus XL XS plus XL the whole square is equal to 0, and this Vs square is constant, so I can take it outside, into differentiation with respect to RL into RL by Rs plus RL the whole square plus XS plus XL the whole square is equal to 0. Okay, so of course this will cancel it. If I bring this thing over here, this will become 0 by Vs square. 0 by Vs square is 0 itself, right? So we will be left only with this equation, and this is basically U by V equation, right? So I'll apply U by V equation over here. So which means V into du. V is this denominator, right? That is Rs plus RL the whole square plus XS plus XL the whole square. This is V into du. Du is a differentiation of RL, which is 1 itself, into 1 minus U into dV. U is RL U is RL into dV is differentiation of the denominator, which is 2 into RS plus RL, and here there is no RL over here, so this is plus 0. So 2 into RS plus RL plus 0, which is 2 into RS plus RL. Okay, divide by the whole, divide by V square. V square is RS plus RL the whole square plus XS plus XL the whole square, and the whole thing is a square, equal to 0. Okay, this denominator has no significance, only the numerator, which means this is basically the numerator is equal to 0, right? So therefore we have RS plus RL the whole square plus XS plus XL the whole square minus, here you have 2RL RS minus 2RL square equal to 0. Okay, and let me expand only this. I'm not touching this, I'm only going to touch this. Okay, I'm going to expand this, so this will become RS square plus RL square plus 2RS RL plus XS, there is no use of expanding this, that's why I'm not touching this, plus XS plus XL minus 2RS RL minus 2RL square is equal to 0. So these two terms will cancel each other, then you have RL square minus 2RL square is minus RL square, which means the equation now becomes RS square minus RL square, RS square minus RL square plus XS plus XL the whole square is equal to 0. Or in other words, this equation becomes, let me see, RL square is equal to RS square plus XS plus XL the whole square, right? Or RL is equal to root of, RL is equal to root of RS square plus XS plus XL the whole square. This is what it means, right? RL is nothing but root of RS square plus XS plus XL the whole square. And what does this mean? What does this actually mean? This is nothing but what is the magnitude? What is the magnitude of this number? See, if I write root of a square plus b square, if I write root of a square plus b square, it means that it's a magnitude of a plus jb, right? In that case, what is the magnitude of this? This is the magnitude of the number. The real part is RS plus, and the imaginary part is j into XS plus XL. This is the imaginary part. So this is nothing but the magnitude of this number. Or I can say that RL is equal to the magnitude of RS plus JXS plus JXL. And what is RS plus JXS? RS plus JXS is your source impedance, right? RS plus JXS is your source impedance. So which means RL is equal to the magnitude of ZS plus JXL. This is what the maximum power transfer theorem is saying for case 3. That is, if you have a load with a variable resistance but a fixed reactance, then if you want to have maximum power, then this variable load must be equal to your magnitude of source impedance plus your plus JXL. Plus JXL, that is your fixed load impedance, your fixed load reactance. This JXL represents the fixed load reactance which you cannot change or do anything about it. Then that will remain over here, and so that you need to add along with your source impedance, and then you need to find the magnitude. That will give you the value of this load resistance. And if this load resistor, since this is a variable load resistor, so if you fix the load resistor to this value, you will get maximum power from the source. This is case 3. Okay. So let me tell you this in summary. So in summary, this is the maximum power transfer theorem or maximum power transfer theorems, right? In the first case, if the load impedance is a variable resistance, then you will get maximum power from the source if that load impedance or the load or the variable resistance is equal to the magnitude of your source impedance. That is, ZL is equal to magnitude of ZS. If the second case, if the load impedance is a variable resistance with a variable reactance, then you will get maximum power from the source if the load impedance, if your load impedance is nothing but the conjugate of the source impedance. Conjugate of the source impedance. Then you will get maximum power transfer. Okay. Now in the third case, if the load impedance is a variable resistance with a fixed reactance, which means you cannot change the value of the reactance. Unlike this, you cannot change the value of the reactance. Then you will get maximum power from the source if, since only the resistance is the only thing that's variable over here, so therefore RL can only be changed. Therefore RL must be the magnitude of ZS plus J is XL. Okay, plus J XL. So these are the three cases you need to look out for when you are doing this maximum power. So basically, how do you do the problem on maximum power? Basically, you said like over here, just like how you see it over here, you need a voltage source with a source impedance in all the cases which you have did so far, in case 1, in case 2, in case 3, in all the cases over here. This is case 2, then you have case 1 over here. So in all these cases, you can see that you need a voltage source with a series source impedance, right? You need a voltage source with a series impedance. So basically, how do you going to find the maximum power of a circuit which does not have a voltage source with a series impedance? In that case, you need to convert that circuit into a voltage source with a series impedance. And the only way to do that, all of you know that theorem you are going to apply is Thevenin's theorem. That is what you are going to apply in this problem. That is, in all the problems related to maximum power transfer theorem is also Thevenin's theorem, because the Thevenin's theorem can basically you can convert your circuit into a voltage source with a series impedance. So once when you convert the voltage source into a series impedance, you will have the value of the voltage source and you will have the value of the series impedance. Now all you need to do is look at the type of the load. If the load is a variable resistance, then the maximum power is when ZL is equal to magnitude of the source impedance, which you have already found when you are finding the when you are doing the Thevenin's problem, right? When you are going to find the Thevenin's equivalent itself, you will find the value of ZS and you will find the value of VS. So in that case, depending on the value of the load impedance, depending the type of load impedance, whether it can be a variable resistance or it can be a variable resistance with a variable reactance, or it can be a variable resistance with a fixed reactance. So in that case, if it is the load impedance is a variable resistance, then this is the value to have maximum power. If this is your load impedance, that is a variable resistance with a variable reactance, then this should be the value of your load impedance. And if your load impedance is a variable resistance with a fixed reactance, then to have maximum power, this should be the value of your load resistance, that is ZS plus JXL. So these are the three conditions. So first you're going to apply Thevenin's theorem to get the equivalent voltage source with the series impedance, and then you apply the corresponding equation depending on the type of the load. Okay. And in case if they have not mentioned the type of the load, can either be variable resistance or a variable resistance with a variable reactance, or it can be a variable resistance with a fixed reactance. So if they have not mentioned what kind of a reactance it is, if they have not mentioned what kind of a impedance, if they have not mentioned it, then you can always assume that it is the case 2. Okay, in that case you can always assume that it is a variable resistance with a variable reactance. You can always assume that it is a variable resistance with a variable reactance unless and otherwise it is not mentioned in the question. Okay.